welcome back. So this is a recap of the stream that we did on Monday evening or Tuesday morning, depending on which time zone you are. And so I've also adjusted the video settings. I've been playing around with this. Part of my goals for the YouTube channel the last year or year and a half has been to, do 10,000 really bad videos. There's this thing that says, everybody has the first 10,000 videos you do are going to be terrible, and so just might as well post them online for everybody to see. Alright, I meant that in a only serious kind of way, obviously. Well, let's see what we did this week. So first of all, let's do a recap of the recap. So in the previous week, we had started running the GMGC. You're not seeing the code. Running the GMGC, which is the Global Microbial Gene Catalog, and we had said, this is a better reference for the kinds of genes that we expect to find in the microbiome. We can select only the complete genes to avoid this issue that we had before of, maybe some of our references seem really small, but in fact it's because they're incomplete. We also had the reference we were using before was UniRef, also had eukaryotic genes, which is not really appropriate for our purposes. So we wanted to check GMGC better. So we wrote code that would run GMGC doing the same KEGG annotation exactly that checkm2 does. And I ran it and it crashed after a few days, or maybe I just let the computer run out of battery or something. But fundamentally it was a little bit of a brittle process because I've said that I want to have everything that I do on the stream, I'm going to be running it on my laptop, so we do have access to some high performance computing. I can run things on machines with a few terabytes of RAM if I need to, but for this project in particular, the extremely open science project, I'm only going to do things that anybody in the world can follow. So this was no longer the case if I was running now, if I would be running things on the high performance computing. So what's the solution here? So the solution was to split up the input. So we adapted the previous code. So here's the previous code, more or less the same as we had before. Conda run, diamond blast p, the same. Just here a couple of adaptations, because before that we also wrote this other function that splits a FASTA file. So it takes an input, number of sequence per chunk, and then there's a couple of details here at the beginning to make everything work okay. But basically we're going to be iterating, and then we count the number of sequences that we have, and whenever we reach this number of sequences per chunk, we start a new chunk. So we split up the GMGC into chunks of 2 million genes, and then once we have each chunk, we run diamond on it. So so this ran over the last few days. So now you can see it split into 48 chunks, and there's the outputs, and you can see that. Let's just look at center here. Here we see some output there. It doesn't really matter what it is. So you can see that from the 2 million inputs that this chunk had, 1.3 million had an output. So in the next session, so on Monday/Tuesday, we'll be just going over what this means, right? So this is a very, very standard sort of jug type of thing I showed, and then let me just see if I can pull that up real quick. Oops, pull that up real quick. Sorry, I don't know what this happens right now. Just wanted to. This is a very standard jug type of process where this fan in, fan out. So even in the original jug paper, we illustrate this. You have especially these fan in, fan out type of structures. So you have an input, split the input into multiple chunks, process each chunk independently, and then collect, and then potentially another fan in, fan out operation, right? And so in our case, this was mostly because this meant that now we have 48 chunks. Each takes about an hour, couple of hours to run, so it's a much more manageable time. And if there was any problem, that would mean that we would only lose a little bit of work and not have to have Diamond start from scratch, right? So this took about the first third of the session, and then we spent the next third looking at updating what we had seen before. So before we had, I'm gonna run the code. So all of the code is on GitHub as usual. So before we were using this uniref standard. This is actually what CheckM2 uses. And as I said, this is not great because it includes partial genes, it includes things we're not really care about. And we had, loaded all of these outputs, done all of this sort of data wrangling. This is a little bit messy code. We would probably have to fix this eventually at some point. Catching positions. Sorry, get this. This was actually a little bit too fast. Eventually we'll have to fix this at some point, but for now it's going to do, just exploratory. And so in the past we had loaded these and then looked at the results of per KO, and we had looked at percentiles. So this would be, so we were looking at, so within each let me, sorry, I just need to add a little bit of magic code there. So we had looked at these percentiles. The problem with percentiles is that in some cases it's not really a very good it's not really a very good example. If a certain KO is very regular, then maybe a percentile, you can be in the low percentile for no, quote unquote, no fault of your own. And so here on Monday we decided to look at z-scores, and then when we looked at z-scores we could see, so here's this is E. coli, so you can see that z-scores, so -2 z-score, so this is kind of a threshold of where things start to be more unlikely. You can see that there's even with 1,000 mutations, which is probably around a reasonable amount of mutations for a bad genome. You can see that it's heavy enrichment here. And so we looked at this. We also looked at the fraction of genes, including the fraction of genes by different limits. So if we take -2 as the z-score limit, so in the wild type there's only 7 genes that have a z-score of -2. So this is actually less than if it was a perfectly normal distribution, but you can see like -6, it's very rare in the wild type, but fairly common in, you see double-digit numbers in after 1,000 mutations. And actually I'm just going to run now over several different organisms that we've been looking at. You can see that this is a little bit more stable than the percentile score. So the percentile scores, we had seen that Campylobacter in particular seemed to have slightly shorter genes, but if we look even Campylobacter, where it's going to, so this is E. coli we showed before, Bacillus subtilis, you can see again slightly different results, but when we look at something like -6, there's maybe here, and Listeria again, very quickly goes to very quickly. And Campylobacter. So if you look at -2, we still see a fair number of wild-type genes with a -2 z-score in terms of size, but when we go to -6, we can see basically 1. Staph aureus, again the same. Still a fair number, -2, -6, that's 0. And there's still some signal. So, and this is still considering, all of the genes, all of the KOs. So maybe once we have, first of all, a better reference, which would be the GMGC. Also, we can maybe start thinking, are there some KOs that are better as references because they're more stable than others? And so this is what we're going to look at next week. So here you can see this is the z-score distribution, sort of, and it does vary between, the different organisms, but this is the 1,000 mutations. It still stays above, and the wild type goes to very close to 0, very fast. So they're across all of them. Okay. So all right. So yeah, you can see here this. I actually don't know exactly which species this is, but it does take a little bit longer. But with -4, again, very very close to 0. So if you look at this extreme left end of the spectrum, or the lowest Z scores, we will probably be able to turn this eventually into something. All right. So this is what we did. So we ran the GMGC, and we've explored using z-scores instead of percentiles. So next week we'll try to put these things together. Use the GMGC as a reference to define what z-scores are, and so everything's on GitHub. As usual, we have a mailing list. So if you're listening to this right now, soon after I record, I know this stays on YouTube and some people listen much later, but so today is September 6th, 2024, and so actually on Sunday, September 8th, I'm going to be in Melbourne. I'm giving a talk at Monash University on Monday the 9th. Actually, I think that's open to all academics, whether you're at Monash or not. So yeah, please come say hi. If you have any recommendations for coffee in Melbourne, people from Melbourne keep bragging about it, and I want to go check it out. So otherwise, I'll see you all on Monday/Tuesday.